Thanks so much for the invitation and the great introduction. So I'll hope I can convince you that it's not evidently crazy and maybe even somewhat rational what I'm trying to do. And I'll start out giving you a little bit of a background why in the world one would want to do it, and then move on how it could be done and maybe close with what you could do with it once you had it. So basically, and I have been saying this here already in a few words before, carbon dioxide in the atmosphere piles up like garbage, and the climate problem is dominated by CO2 from fossil fuels. And keep in mind, there is no simple decay time for it to go away. As a matter of fact, after 100 years, roughly half of it is still there, but then it slows down. It's more like a diffusion process than an exponential decay. So the time constants get longer and longer. If you come, the warming lasts approximately 1,000 years. If you look at the combined ocean biosphere atmosphere system and ask how long will that excess carbon persist in there, geological weathering eventually will take it out, but that's tens of thousands of years. And so in a way, and this is where I started in the early 90s, in some ways one has to think about this as a waste management paradigm. It's just like sewage in the past. We are dumping the stuff in the atmosphere and we ignore it. And the first thing we need to do is stop doing that and then clean up after ourselves. And one of the points I will make today is I think it's probably too late to just say we stop, because by the time we actually successfully stopped, we still have a substantial overhang and we need to figure out how to get rid of this. And I would argue there's really is a substantial shift in paradigm. If you think about it for a moment, if I left my garbage in front of your house and you call the police because you don't like it, and I say, but you should praise me because it's 10% less than last year, you immediately notice that we are not treating carbon dioxide like waste right now, because this is exactly how we manage it. Yes, it's a very good thing to reduce our emissions. It's a very good way of trying to reuse it and recycle it. I would like to point out we are producing more CO2 in a year than we produce aggregate, gravel and sand. So it's actually very, very hard to make good use of all of that. And so I think first and foremost we have to dispose of whatever we put out, and then in the end we can figure out that will set actually a value to it, because now if you reuse it, you avoided the tipping fee you would have otherwise have to pay. And zero waste is a long-term goal after the cleanup, right? And so we need, in many ways, we have to convince people that that's actually the right way to think about it. And you have to also convince corporations who are in the sustainable business not just to buy renewable energy, but also clean up after the CO2 that their trucks emit when they drive from one place to the other. And in a way, you may have to literally create a movement around it, just like recycling created a movement where people started from the grassroots and moved up to there. Another way of looking at the problem is you can think of it as a budget, right? A little bit of garbage out there might be okay, but eventually we reach a point where we can't have it anymore. And if you listen to the Paris Agreement, we should hold warming below 1.5 degrees, or at most 2 degrees. And if you look at the promised reductions we have right now, they sound more like 4 degrees C. And if we follow business as usual, it's probably going to be 6 degrees C. And I would argue, and I'll make a few points about this in a second, we actually cannot stop in time anymore. We probably rolled already over the 1.5 degrees. I realize we are only 1.1 degree right now. But keep in mind, if we stop tomorrow, there's still inertia in the systems. The oceans are still warming up. And the 1.5 degree may already be baked in. And so the IPCC has pointed out that if you want scenarios which stabilize in that window, you will need, in nearly all of them, substantial amounts of negative emissions, which means decades of time in this century where net total we are taking CO2 back rather than putting CO2 out. So in a sense, we have to figure out how to get it back out of the air. And by the way, store it somewhere safely and permanently, because if I made fuel out of it, 3 weeks later it's back in the atmosphere and I kept things level, but I certainly didn't come back down. Right? And I would argue these carbon constraints put rather serious constraints on where people are. By the way, I thought I had changed this number. It's actually around 25 25 tons by now. I made that slide a few years ago. I need to correct for it because we per capita put out another 5 tons over the last 6-7 years. And this truck, just to give you a feeling, has 30 tons of carbon in it. So if you next time you fly somewhere, that came out of your personal allotment when that tanker truck fills up your airplane. That's what everybody has for a 7 to 8 billion people population before we hit 450 ppm, because you can simply lay out a budget where you can say, roughly speaking, that's what you have. So from my perspective, and this is where I started early on, for every ton of, because the big box is very simple, the big control box, for every ton of carbon coming out of the ground as fossil carbon, another ton of carbon has to get back out of the system, because otherwise we can't possibly balance the books, right? And I would argue all carbon dioxide emitted to the air will have to be recaptured. Now, this could be via biomass. I'm agnostic at least for this point. But I would also point out, whatever you put in the atmosphere, it doesn't really matter whether it was biocarbon or fossil carbon, because it won't come out of the atmosphere by itself unless you pull it out. Now, you can pull it out with biology, or you can pull it out by technical means. So as I said, you have a carbon budget. Let's just figure out how big that is. If you want to stop at 450 ppm, which sort of many people have suggested is sort of a natural stopping point. By the way, most of the modelers now have you between 450 and 500, and I think there's a trend. The closer we get to 450, the further that number moves out a little bit, because we are sort of giving up on the lower number. But you have 42 ppm left. That's roughly 630 gigatons of CO2. I make a rough conversion that roughly half of the CO2 stays in the atmosphere, the other one is in the ocean. So rather than giving you 2 gigatons of carbon, I give you 4 gigatons of carbon per ppm, or 15 gigatons of CO2. That results, by the way, in an annual increase of 2.5 ppm, which means we are blowing through this budget of 630 gigatons if we don't increase emissions in about 17 years. So I see no practical way we make this happen. By the way, the last few years, everybody was happy to announce that the CO2 emissions from fossil fuels, at least, didn't go up. Interestingly enough, the increase in ppm kept accelerating through this, but last year the CO2 increased, the emissions increased too. So we are still on the gas pedal rather than on the brakes, right? And we need to stop, right? And so things accelerated again, and we need to decarbonize exceedingly fast. Here I did a very simple-minded back-of-the-envelope calculation where I said, how fast do we have to lower the carbon intensity in the world in order to stop at 450 ppm? If you every year reduce by the same percentage, you're following an exponential decay. So I can calculate the decay rate I need to have and work it back out. So what I'm plotting here is the annual percentage rate I have to come down. I'm allowing, by the way, a 3% annual growth of the world economy. So I effectively add 3 to every number in order to see where I come out in this budget. And what you see, if you want to stop at 450 ppm, you need to reduce emissions, the carbon intensity of the entire world every year by 8.5%. And that puts you on a warlike footing. The US did something like that in other economic sectors during World War II. But normally you don't see that happen. By the way, I'm pointing out here, even if you wanted to stop at 700 ppm, you would have to reduce every year by 3.8%. The 3% comes from the fact that you have to overcome growth. But my point is, we have never, ever reached that number in the last decades, because we simply grow too fast. So the bottom line is, I think the 450 may not be technically yet in the rearview mirror, but I think there's no way we can stop that anymore in time. So the other way of looking at this is, I did some very simple thing. I looked up how much coal, how much oil and gas we use, and how much they variously contribute. And I ascribe a rough lifetime of infrastructures in those. Coal plants last 50 years. Lots of oil infrastructure actually only lasts 20 years because there are cars built into there. And gas is probably more 30 years. If I work it all out, the average lifetime of what you have there is 34 years. If I say half of this, which is probably pessimistic or overly optimistic in a way, half of that, most of the stuff is still in its younger half, so there are at least 17 years left. Well, that means that current emissions of the existing infrastructure will be enough to drive us past 450. So we will have to abandon or fix existing infrastructure, leave alone everything else we do from here on out has to be done. So when people say, well, we reduce by 10 or 20%, we are missing the boat. We really have to stop, right? And we will have to overshoot in the stop in order to come back on the other side. And that actually then drives you to having negative emission technologies in some form or another. And they can then compensate for the nearly unavoidable fossil fuel use for a time. We will take decades to stop and phase out fossil fuels, even if we work on it as hard as we can. And we clearly act too slowly right now. On the other hand, we can't go too fast either, because if the energy system collapses because we were too aggressive about it, that will be catastrophic too. So we have to figure out how to stop as safely and fast without spinning out as fast as we can, while at the same time moving into an entirely carbon neutral renewable energy system or a nuclear-based energy system. And then we have to recover from an overshoot. And we can argue where we will stop or where we should stop. If you listen to Jim Hansen, we should probably go back to 350 ppm. I have friends who tell me we should go back to 280, right? But 400 ppm, that might be safe. I think you guarantee at that point that Greenland will keep melting. 450 ppm, that's sort of where the IPCC says we should really don't get over. I just told you we will, so give or take, I think we will have to come back by 100 ppm. If you translate that into gigatons of CO2, that would be, by that same simple arithmetic, be roughly 1,500 gigatons of CO2, or put it somewhere between 1 and 2 trillion between 1 and 2 trillion tons of CO2. So that's the challenge in front of us. By the way, put this in another perspective, 100 ppm or 1,500 gigatons is more than the entire emissions of the 20th century. So this is not a small correction anymore. This is a very serious piece of work where I'm telling you this is what would have to happen if we abandon fossil fuels as fast as we can. If we fail to do that, because people call this a moral hazard, and we keep going, this number will rise with every 30, 40 gigatons we put out every year, because that just adds to the budget, right? So that is the challenge in front of us. And so you need to figure out how to get to a trajectory like this. By the way, here I put sort of just by hand a little more than 100 ppm, getting back to about the 350. That may not be all that far from where we end up. And in many ways, we should stop arguing where we need to stop, but to minimize this overshoot as much as we can. In other words, bend the curve as fast as we can and minimize the peak and minimize the duration of that, because we will have real damages whether we like it or not. Sometimes I make the analogy, we are in a car which is going way too fast and there's a curve. We are going to hit the guardrail. It's not a question whether we will hit it. The question is whether we will break through it or roll over, or whether we get this car to a stop with a fender taken off. But we won't get out of that without an accident anymore. So if you want to remove the carbon from the environment, what are your choices? The first one, you can collect it from the biosphere. That's where people say, well, we can grow forests, we can do afforestation, we can put it away as biochar, we can bury it in the deep ocean with ocean fertilization. People have suggested that. You can do BECCS, bioenergy with carbon capture and storage. All of those options are there. And you can collect it from the ocean. And that's a huge, huge reservoir of dissolved inorganic carbon. It's in very close contact with the atmosphere. So if you take it out of the surface ocean, you are also taking it out of the atmosphere, and vice versa. If you take it out of the atmosphere, you will also take it out of the ocean, because the two systems are in tight equilibrium. And so therefore you have to get it all back, whether you like it or not. I prefer the air over the ocean by a simple observation. The dilution of carbon atoms, carbon molecules, dissolved inorganic carbon in ocean is 1 in 25,000. In the air, it's 1 in 2,500. Now, the density of that carbon in ocean water is a lot higher, but there's a lot of more water in a cubic meter of water than there is air in a cubic meter of air. So the net result is, in the ocean, you are 10 times more dilute than you are in the atmosphere if you measure it atom for atom. I would argue biological capture can simply not reach the scale you want. If we are talking about 30, 40 gigatons a year, which you would need for 40 years in order to come back 100 ppm, I'm not talking about balancing an existing budget, I'm talking coming back. If you wanted to get to that scale, you are more than doubling the agricultural land in order to just have enough sunshine to pull that off. So I think at that point, your environmental footprint of that becomes very difficult. You could increase the ocean sink. I think you are starting to talk very serious environmental issues. So I believe that the most benign, not entirely benign, but most benign option on the table is to pull the CO2 by some technical means, and we'll discuss what that might be, out of the atmosphere, and then do carbon capture and storage with it. Alternatively, you can, rather than DAX, direct air capture and carbon storage, you could also do direct air capture and utilization, which presumably means you make fuels and plastics. And I don't think you will hide all that much carbon from the environment, but you at the very least can have a renewable energy infrastructure which is based on recycled carbon. So you can close the carbon cycle that way with solar energy or nuclear energy, in any case a carbon neutral form of carbon-free form of energy, which then creates fuels just like you would, which then become an energy buffer. And if I fly again from Arizona to here, I could actually claim to be carbon neutral. So air capture then becomes part of a larger picture where you say we need to store the carbon. You need fuel synthesis and make chemicals, and you need direct air capture. I think those are sort of the basket of technologies you need to come up with. I would argue this has been studied to a large degree. It's not very popular. I think we can't really change that, because if we really have to find a home for 1,500 gigatons, we better figure this out. And I think there are established technologies. Look at what Statoil does at Sleipner, but they are no means at scale. I mean, people put a few million tons, maybe 50 million tons of CO2 is injected underground for various purposes per year right now. We have to go from 50 million to 30 billion, and that's a big jump, right? And fuel synthesis, we know how to do. It has always been too expensive. If photovoltaics and other renewable energies really get cheap, you can do that. If you have a direct conversion, you can do it too. Those are all equivalent processes, but you need to figure this out. And once you have reduced the carbon to CO, or you have reduced water to hydrogen and oxygen, you actually have all the building blocks, because people know how to do the next steps. Now, they are still not technically ready for mass production, but they exist. We know how to do Fischer-Tropsch. We know how to make methanol from hydrogen and CO2. We know how to make methane. All of these things are known, but nobody has ever built a real economy around that. And then lastly, you need direct air capture, which is, of course, a very novel technology. We have just barely introduced, and it needs demonstration and scaling, right? And it needs to be shown to be cost effective, because if it isn't, we are wasting our time. So air capture, I would argue, for that reason, is an enabling technology, sort of that missing link in that story. And so you could have one story, and this is where we get unpopular. You can pull fossil carbon out of the ground, you make your hydrocarbon, you capture the CO2, and you bury it. The alternative is to close the cycle by picking up water and CO2, synthesize the fuel with renewable energy, come back around via air capture and keep this cycle going virtually forever, right? This is a truly closed cycle, minus the gallium or whatever platinum catalyst I'm burying in here. But apart from that, there truly is a renewable story. So you can use air capture, and I would stress one thing else: it removes all exceptions. Right now, in most countries you go and they say, well, yeah, these evil coal plants have to deal with their CO2, but the airplanes, we really don't know what to do with. Well, if you can capture from air, all carbon is equal. Right? I don't care anymore how you emitted it. I can always get it back. Now, if you're a coal plant, you may have a smarter way of doing it than first letting it out in the air and running after it. But that airplane has no excuse anymore if you do this. By the way, the coal plant not either, because I have heard coal executives say, well, we understand that this is a problem, but we need to research it a long and hard time because it's so hard to do and it's going to be way too expensive. If you could cut through this and say, for $80 a ton, you can do this. So do it. If you can't figure out how to do it better, you'd be surprised how fast they actually be faster than that. So you can think of the air capture, particularly the way I'm going to do it, which is standing passively in the wind, literally like a mechanical tree. It just stands there, the wind blows by, and the CO2 is being absorbed. By the way, the typical designs people talk about, given a given size, are about 1,000 times faster than a tree, because they can seriously, with an individual device, pull the CO2 down, whereas the removal rate of a tree is nearly imperceptible. If you stand on the downwind side of a tree, the CO2 concentration in the air is not noticeably different than it was upwind from it. You can collect current and past emissions, and that's of course important because now that they are in the air, you can get them from there. You can deliver the CO2 for disposal or fuel synthesis. You can operate at a global scale, and I will make that case a little later, that you could literally get to that 40 gigatons a year. And the air will transport the CO2 to where you want it for free. So you don't need a large pipeline system to get the CO2 where you want it. You would place yourself where you want it, and therefore there's no need for pipelines anymore. Yet, I would argue, it has been very difficult to get acceptance for this problem for a variety of reasons. Particularly if you live in the US, there will be skeptics who tell you there's no climate change, why do you want to do that? Right? And although I found it very interesting talking to people in Arizona, where this is far more common than it was in New York, that you can actually convince them on the waste management story. You can say you are dumping, for every mile you drive, you dump a pound of CO2 in the air. And they say, well, that I shouldn't do. And never mind whether it causes climate change. And I think there are still plenty of people who say, well, if we stop, the CO2 will go away. And you hear it actually often in conversations. People say, we need to hold emissions constant. No, we have to drive emissions to zero if we want to fix the problem. Right? And if we're already too late, then we have to go below zero. Right? And then there was a paper in a little more than a year ago in Science, which was titled "The Trouble with Negative Emissions," and which is ultimately about the moral hazard. People say if you can do that, then people won't change their lifestyle, and people will not stop using fossil fuels, and therefore you shouldn't do it. And I would argue this was a very nice argument in 1980 when we had time to fix it. By now, we are not hesitating anymore and waiting to put a delay in. The delay has happened, and now we have to figure out how to come back, right? And I think you see among renewable, there's a zero-sum pie, and if you guys do that, then we don't do our stuff. And I would argue we are actually allies, because we can deliver a way of buffering the energy in the renewable system, because we can become a flexible consumer. We can pick up electricity when nobody wants it and make fuels out of that by giving you the carbon you need to make it, right? We enable renewable energy to penetrate far more deeply into the system. You could literally have an all renewable system which takes its excess and converts it into fuels. Some of these fuels will be used when you don't have renewable energy or you're falling short of it. And the other part could go into the transportation sector. The aviation industry will need jet fuel of some sort, because I can't see us flying an airplane with a battery. The battery is simply too heavy. And I think in the oil companies, for a long time you heard, we don't really want to deal with this. We are happy to take the CO2 from coal, but you need to leave us alone. And we changed that. But I would argue their attitudes are changing right now. So I think we may very well see that story is changing. And then lastly, and this is prevalent in many engineering groups, it's just not feasible. Economically not feasible. And I heard that today it's energetically not feasible. And so we need to look at that. And the typical argument brought forward is known as Sherwood's rule, which says if you have to separate two things, the cost scales linearly in the dilution, and if that's true, then we are indeed in trouble. So we have to figure out how to get around it. And I admit what we are doing in many ways is a technological fix, and so I found it interesting. There was a paper some years ago in Nature which looked and analyzed technological fixes, and it explicitly talked about air capture, and it said a good fix must largely embody the cause and effect relationship. And they said that down here, you can read it yourself. Well, air capture does that, right? The effects must be accessible. That's also fairly easy, because here's a ton of CO2 I just delivered to you, right? And it must be solvable. And they said, they in here argue it's rather surprising that people don't push it harder, because it could solve the problem. And so, but the question to answer is really that third part. Can we actually do it? And the first point I would like to get across there, air capture is not flue gas separation, and it's not a simple extension of flue gas separation. And I think that's what has gotten us in trouble, because people say, well, if we can know what we can do here, now what could we do there? And it becomes therefore too difficult, too costly, not practical. And the first estimate said $600 a ton. And I would argue that $600 a ton is actually the glass is half full rather than half empty. And I'll discuss that in a minute. So the dilution is too extreme. Sherwood's rule was brought forward, and the cost scales linearly with dilution. And if you look at what it costs in flue gas, and I'm 300 times as dilute, I can't possibly afford paying 300 times as much. But I would point out that the APS study at $600 falls way short of being 300 times $100. So $30,000. So even they violated Sherwood's rule to get to this number. And my view is, don't try to extrapolate. You really have to start from scratch and think about it. And by the way, I put the penguins there because I was interviewed after this APS study came out and said, what do you have to say to defend yourself? And I said, well, I read it. Everything they said is exactly right. And they are a little bit like fluid dynamicists or aerodynamicists who now carefully prove that penguins can't fly. I have no disagreement with that, but you shouldn't generalize it to that birds cannot fly, right? We need to figure this out, and I think you really have to think out of the box, because if you take the standard technologies you have in flue gas scrubbing, it's like converting that locomotive into an airplane, and it won't work. Right? So you have to start from first principles. And in a way, the inspiration comes from nature. So if energetically it's really impossible, by the way, then the tree should not be able to do it either. Right? But the tree can do it. So you know that it is energetically feasible. And you could, when people said heavier than air flight is impossible, you could look out of the window. There were birds out there, and they were definitely heavier than air. Right? So we need to figure that out. And here's the challenge. CO2 in air is indeed very dilute. And let me throw in another one. I have never heard the critics state, but it's right nevertheless. The air is full of water. And most things which can bind CO2 will happily bind water. And if we get into the business of collecting water out of the air, and we are proudly can collect a ton of anything at $30 a ton, which would be a really good number for CO2, for water it's a disaster. Right? I can buy water at 20 cents a cubic meter. Right? So I can't afford becoming a water collector. Right? Then you have Sherwood's rule again, and first of a kind will be expensive. We will have to overcome that. So, but I would argue the CO2 in the air is not too dilute, and I give you a simple back of the envelope. If I give you a cubic kilometer of air and I say we have windmills, they are demonstrated, they can collect CO2, they can collect kinetic energy out of the air. And if I go to a place where you have 6 meters a second wind, you have 20 joules in a cubic meter or 20 gigajoules in a cubic kilometer. And I can therefore say if I gave you 5 cents per kilowatt hour of kinetic energy, that's the value of what I'm mining. I have $300 worth in a cubic kilometer. By the way, that windmill sees this in a few hours. If I'm giving you a tipping fee of $30 for recovering a ton of CO2, that same cubic kilometer has $21,000 worth of CO2 in it. So it's not too dilute. I may still not have a good idea how to do it, but in a roundabout way, that got me going, although I, coming from physics, didn't think in terms of monetary numbers, which I gave you right here. I instead thought of energetic numbers. I said, well, the CO2 has an energy equivalent because if I were to collect the CO2 out of a cubic meter of air, I'm allowed to put it back in by burning a thimbleful of gasoline. Let me work out the heat of combustion of that. It's 10,000 joules. The kinetic energy at 6 meters a second of that air was 20 joules. So in this case, I got a factor 500 between the two. And that actually, this diagram, on a napkin actually, that diagram was the starting point for me to get involved. I said, if I have such a lever arm, I should figure out how to make this work. So people have argued it's thermodynamically impossible, and also told, because I said it's RT log P, which is of course not right. They said, you don't even understand the thermodynamics. So here's the official, correct, free energy of mixing of two ideal gases with a partial pressure of P1 and P2. And I'm assuming you have an air with a total pressure of P0 coming in. You have P1 of CO2. You come out with pure CO2 at the same pressure, and you come out with a residual pressure P2 in that. So you have P0 minus P1 is the rest of the air. P1 is the CO2. I make pure CO2, and I give you CO2 somewhat lower in the air than before. This is the correct formula. You can read the paper. Every textbook has it too. So I've now gotten interested in the skimming limit. I'm saying I'm not taking all the CO2. I just skim off the first few ppm. Right? And that's easier. And so I did some simplification of the formula because now I can say P2 approaches P1. I simplify my logarithms by expanding them. I plug it in, and guess what? I just got RT log P. Right? Because that's what's left of the complicated formula if you take that limit. So, having said that, I observed that virtually every capture method for CO2 from air is sorbent-based. And that's not terribly surprising because there's lots of air and very little CO2. And I can't afford doing anything to the air. I can't compress it, I can't heat it, I can't cool it, I can't do anything to the air because there's 2,500 times as much as there is CO2. I can put a sorbent in its pathway, and the CO2 will just stick to it. It actually releases energy at this moment, and later on I have to pay that energy back. So I need a binding energy which matches that delta G. Right? All air capture is chemical sorbents because physisorption is just not big enough to make this work at 20 kilojoules per mole. Right? 22 kilojoules per mole. All air capture sorbents I'm aware of exploit carbonate chemistry. So these are hydroxides, carbonates, and they go to carbonates or bicarbonates. So then if I have a single sorbent which has one strength, I have to overkill because it has to absorb down to the level I want to absorb to. So this is the free energy function you saw before. This is the free energy of binding a sorbent will need, which can get down to this level. Notice if I only take half of it, my efficiency is nearly 95%. If you want 90% of it and you are out here, you are about 50% efficient. So in a funny way, we are actually already better off than the flue gas scrubbers because they need to get all of it because that's the CO2 they are after. I have an infinite amount of air. I can get only the part I'm after. So you see this here. I calculate RT log P over P naught, where now P is the pressure at which I give up and I don't care to go down. So in the air, I come down to half of the concentration in the air. That's your 22 kilojoules per mole. at 300 Kelvin, and then I'm making the argument that that power plant actually was a little hotter, 70 degrees C or so, and I'm somewhere between 99% and 90%. So I'm here in this 15 kilojoule per mole range. So we are 1.5 times what those guys have to pay. So we pay more energy, but not orders of magnitude more. So where did that big multiplier come from? Because what I'm observing here is effectively, from an energetic perspective, I have to pay very little. By the way, put these numbers in perspective. When I combust gasoline, I get 700 kilojoules per mole. So this 22, as well as the 15, is a very small number. So the Sherwood's rule got us in trouble because people say $30 for a ton of CO2 at a power plant, you are 300 times as bad, so you're $10,000 a ton. Right? And Sherwood, in the original paper in 1957, he mentioned it. Here's a National Research Council study from 1987 where they drew a plot where they said, isn't it remarkable? If you look at minerals, every mineral, the price of a metal is about $10 per ton of ore. And that's your linearity relationship. It depends on the dilution, how expensive you are. By the way, they made the same case for pharmaceuticals. And if you think, this had bothered me long before I thought about air capture. And I wanted to understand how come the thermodynamics tells me it's logarithmic, it's always linear. And the reason is actually quite simple. You can ask yourself, what in the world can I actually do for $10? Well, I can dig up a ton of rock, that's about $1 or $2. I can crush it and grind it, now I'm at $5 to $6. I can run a flotation, now I'm 7 or 8. And these are earlier numbers, probably double today. And I can end up getting rid of the tailings. I just spent $10. Which basically says the first step in the process is what's costing me money. And if the first step dominates my cost, it's of course linear. If you told me there's only half as much in there, I'm crushing twice as much rock. So therefore I end up paying twice as much. So it has to be true. And given that it's only $10 per ton of ore, I basically have no budget for converting copper concentrate to copper or platinum concentrate to platinum. That must be in the noise compared to the first step. Otherwise, the relationship. By the way, you can get to these here. They are all coming. The pharmaceuticals all come from fermenters, and I bet you this is the price of making beer. And then getting down to the concentration you were at in the original broth. But bottom line is, I can explain Sherwood that way. We are, and I put it at $20 a ton here as ambition because I'm deflated the inflation back out in order to get to 1987 numbers. And you see how far we are below, and that's why we are in trouble. Here is somebody who actually did it. This is uranium from seawater. And uranium in seawater is 3 parts per billion. Not 300 parts per million, 3 parts per billion. And people said, well, we have certain resins which absorb uranium out of seawater very happily. And they made this work in the 70s, and they couldn't pay for it because they couldn't pay for the pumping energy. Right? Which is classical Sherwood. It's the first step, right? You're pushing all that water through the filter, and that's where your energy went. And so then in the 2000s, a Japanese group came up with the idea. They said, we are going to use artificial kelp. We are making strands of the resin, anchor it to the ocean floor, and let the water flow over it for 6 months. And then we harvest it. So they suddenly removed nearly all of the cost of the contacting. And thereby, that cost dropped out. Now it was just the cost of processing the sorbent. Once you have the uranium on the sorbent, you have completely forgotten how dilute you were, except that you remember the binding energy. And that's logarithmic, not linear. So they ended up beating Sherwood by a huge, huge factor. And we are arguing we are doing the very same thing. You have to be passive in order to make this work. In a way, the cost has a linear term. That's the contacting. It has a term B plus C log D, which is your thermodynamic price. And you better make sure that that A is small. And they made it small by being passive, and we can make it small too. So as a result, we can walk around Sherwood's rule. It's not a law, it's a rule, and it's a rule of thumb which can be broken. And here you see the problem with it. this is the gigajoules per ton of energy I have to pay in order to push air through a filter against the pressure drop of 100 Pascal, 250 Pascal, 500 Pascal. And by the way, this is what I can afford, a gigajoule about. Anything beyond that I can't afford. And what you see here, that the pumping cost or the blower cost is eating my lunch if I turn them on. And that's what you need to avoid. So then the sorbent has maybe 30, 40 kilojoules of binding energy, and it's manageable. So in short, you can make an analogy between wind collectors of kinetic energy and CO2. And the argument is, at the end of the day, I'm predicting that as the technology matures, our cost will be always slightly higher than the perfect flue gas scrubber, but not orders of magnitude, because our energy is about 1.5 times what they have to pay. So therefore, I was interested in pushing this further. Today it's actually real. Somebody mentioned Kleinberg's in Zurich, which is, they are running blowers. Carbon Engineering is running blowers, and they spend an awful lot of energy because they're using a very strong sorbent potassium hydroxide, and then they spend a lot of effort to separate it apart again. But they have gorgeous kinetic as a result because they have such a strong sorbent. And Global Thermostat is a company in there, and there are a bunch of universities looking at it from various angles, and we are in that game too. Here's what we are currently building. This is a device. Think of these things as, this wide, this tall, and they have little passageways where the air can blow through passively, and then they collapse into a box. You see it actually down there, where we spray water in it, and then we recuperate the CO2. What we stumbled into, apart from being passive, we stumbled into an anionic exchange resin, stuff you buy routinely for salt, routinely for softening salt, water softeners and things like that. Stuff is relatively cheap, and we take an anionic one, so the cations are fixed to the polystyrene, so you have an quaternary ammonium ion here attached to a styrene. And this has a remarkable feature that when it's dry, it has a very high affinity to CO2. You can literally drive the CO2 in air down to 1 ppm or less. But if you make it wet, it doesn't like the CO2 anymore, and it gives it back. And you can see this in this chart. So here is the saturation of the resin. At zero, it has no CO2. At 1, it's fully loaded. And this is at 21% relative humidity and room temperature. You see it loading up, and at 400 ppm, which is, these are Pascal, 40. At this level, it's basically loaded. If you now expose it to 100% relative humidity, or make it literally physically wet, either one will work, you jump up on this curve, where the partial pressure over the same loading is 500 times larger. So this gives us a cycle. We can load up as we dry in open air, then we make it wet, jump up to this cycle, let it go until it doesn't, it's empty enough, then we put it out in the open air again, it's dry, and it loads up again. So we need to come up with this thing that can do this. This is an early device where we tried things. This was already in Arizona on a roof, so you have these filters. This is after months exposed to the harsh sun. We actually took the roof off for a good time to see how it would survive. And so the air flows through there. Then here's the chamber where it's made wet. You see it's sort of foggy in there. We maintained like 2% CO2 in that bottom chamber for months on end, while this stuff, when it's open in the wind, is drying out. Here's another filter we designed to make this happen. Here you see a bunch. This is a small test device inside the lab to do it. And here is the version you saw in the shop in an earlier picture, now standing out and feeding an algae pond to give it CO2, because the algae wants CO2. And here you see our next design, where we basically make a circular column where the horizontal slots in between those discs, think of it like an old vinyl disc stack, pulled apart, and then for regeneration it drops into this chamber, and we'll spray it with water to induce it, to release it. We can pull a vacuum in there while we do it, or we could just sweep it out with air if for example we were to feed it to a greenhouse. Yeah.
There's more water vapor in the air than CO2. How come that?
That's a very good question. The point is, this is a sorbent which has two different sorbates, in this case H2O and CO2. And it turns out, we worked this all out, this is a whole thermodynamics, it's another 2-hour class, but the bottom line is they strongly interact. And it turns out if you make it all the way wet, water coming on pushes CO2 off, and CO2 coming on pushes water off. So somewhat, and so when we are inside, we are exposed to 100% relative humidity. Out here, we were 20% relative humidity. We are in Phoenix, after all. So now it picks up more water, and therefore it doesn't like the CO2 anymore and pushes it off. Then we come back out. Now it sees 20% relative humidity. The water comes off, and the CO2 comes back in. The energetics of the thermodynamics of this works because we effectively took water from 100% relative humidity and expanded it out to 20% relative humidity. And it's that energy which is released in that step, which is the driving term in our system. And it gives us about 30 kilojoules per mole, which is all we need to enrich the CO2. But we cannot get past 5% of an atmosphere of CO2 because at that point I'm water saturated. Right? So we have to have a boosting step. Put another way, we are making extremely clean flue gas in this box. So taking a mathematician's approach, from here on out, the problem is solved. Right? Because your gas-fired power plant has about the same concentration of CO2 than we have. And I stress this now, we have actually spent virtually no energy. Yes, there's a little bit of energy in equipment moving up and down, but we were passive in the wind. We didn't spend any energy on that. And we evaporated water in lieu of energy. So living in a desert, people there are familiar with the concept of a swamp cooler, which is an evaporative cooler for climate. We are a glorified swamp cooler. Right? We are taking exergy out of the fact that water evaporating into dry air gives us energy. The dumb luck in the process is that the chemistry of this resin connects the two things. And I can give you a lecture. It took us 5 years, but we figured out how it works. I don't know what happened there. So basically, I just said all of that. Let me now go. Here is our latest design. Colleagues of mine called it a Tiburio because it looks like the little tower in the center of a church. We harvest the CO2 by letting the air flow through. We drop it in the box. Now it releases the CO2. This right now is a on-paper design. What you saw before, they were photographs of a really working design. This will be just working much better. We have the moisture-sensitive sorbent, and we have regeneration by simply going in, and we can evacuate this, and then we pull out 5% of an atmosphere of essentially CO2 and water vapor. And the other alternative is to come back with nitrogen and oxygen and CO2 and do a second stage separation. Here's a little one which could directly feed a greenhouse. In this case, you would simply pump greenhouse air from the inside through it. We have actually demonstrated that that works because the high moisture inside a greenhouse is enough to knock the CO2 off this device. We also have a way, and there's a long story I don't have the time to get into, where we basically suck the gas out, dry it, compress it, spit out residual nitrogen and oxygen, although this should only be evacuated first, then compress the CO2, and we came up with a very clever way of storing the energy in this process by having basically frozen dry ice sitting there waiting to melt. And we can therefore run against the solar panel, which only runs certain parts of the day, whereas we run for 24/7. So I think we have a system that can work. Our estimates are that probably the first of the kind is somewhere between $100 and $200 a ton, which puts us a little cheaper than the Kleinworks guys, but it has to be built first. We are still conceptual on paper, and we would love to do the engineering, and we need to raise money, by the way, to do that. But I see us going to a mass production paradigm rather than scaling up. And the observation I start with that a car engine is 100 times cheaper on a kilowatt basis than a power plant. It doesn't last all that long, but it is 100 times cheaper to begin with. And here you see the learning rate in PV, which is literally 100 times cheaper today than it was when it started. So coming up with the $600 being half full or half empty, I would argue it's half full, because you can come down, you need to come down a factor 10, and you're from 600 to 60, and at $60 a ton you are interesting. That would add about 15 cents to a liter of gasoline. So at that scale, it's actually not all that expensive anymore. If you wanted to keep up with current emissions, and I'm not saying this because I think air capture will do all of that, but I think air capture, which would operate in order to come back down 100 ppm in 40 years, would have to operate at that rate. If you could do that, you would need 100 million units, because that's 36 gigatons a year. Is this feasible? A unit like this would fit in the back of a truck. The wind area is about 60 square meters. We built 80 million cars in a year. And that number is dated. It's predicted by the end of the decade to be 100 million. If you last 10 years with your 100 million units, you have to build 10 million every year. Shanghai Harbor processes 30 million full shipping containers every year. So clearly there's an industrial production capacity right behind Shanghai, which is bigger than what we would need for the world scale of CO2 capture. So I think there is no argument which says we couldn't scale up to the scale you need to be. I'm not telling you it's cheap. If it costs $30 a ton for the CO2, which is a very, very good number to get to, you still have $1 trillion revenue in this kind of an enterprise to pull 36 gigatons out. So this is big, but I don't think it's prohibitively big at a scale we couldn't get to. And I think there's no significant limits to the scale. And the reason behind that is the air mixes so fast and so well that theoretically you could plaster the state of New York, the state of Arizona with these devices, and you could pull all the CO2 out there. I'm not advocating it, but you could compress them into an area like that, but you also can take out all the CO2 in Australia. It doesn't matter where you put them. You put them where you wanted the CO2 in the first place. And the amount of air you actually process is orders of magnitude smaller than what a windmill would process. So, and I would argue, and I will argue this in the closing minutes, that you could actually, with mass manufacturing, penetrate the market in decades, because there are plenty of examples where you have seen this. To the cost, here was the APS study, which manifestly studied a process which said of itself, we are not trying to innovate anything new, we take off-the-shelf pieces. And they came out at $600 a ton, and they certainly didn't try to convince people that it works, because they said it can't be done. Early implementations, the Kleinworks is about here. I think you can readily get here. We probably will be here. If I just add up all of our raw materials and translate it into a price a ton of CO2, so this part capital, part I'm paying for all the steel, I'm paying for all the resin, I'm paying for the water, I'm paying for the electricity, and the heat I might use in lieu of electricity. I add all of that up, my cost is somewhere between $10 and $20 a ton. I don't think you will ever get that low, but maybe you can get to twice that number before you asymptote out as you learn. And so I think learning curves are powerful and could get you there. So to remind you, we can draw the CO2 down, we can capture CO2 to make non-fossil liquid fuels, and we can also compensate for the liquid fuels until they got out of the system. And I think as a waste management industry, it could actually be quite lucrative, because it's $1 trillion revenue you would have to generate to make it happen. Then the question is, can you convince people to pay for it? But you see severe carbon constraints in the EU. I just heard earlier you were talking about 40, 50 euros a ton in carbon taxes. The US, by the way, just created a tax credit, in spite of Mr. Trump, a tax credit in the last budget for CO2 sequestered at $50 a ton. That's not a payment, a penalty, but it's a carrot rather than a stick. But if you can figure out to put at least 100,000 tons of CO2 underground, from air capture, by the way, is allowed explicitly. It talks about in the law air capture facilities. You can get $50 a ton for that. So you're starting to get all of this in place. So you in the end you mine the CO2 for air, right? And you can do with it what you want to do with it. You can mass produce, you eliminate the need for CO2 transportation infrastructure, you open remote sites for CO2 sequestration. Oman has beautiful places to make carbonates out of CO2, but not much CO2, but except from the air, right? And you can create negative emissions at a vast scale. How long would it take? I give you here a few examples of big technologies, and I give you 3 numbers. The automobile started sort of in 1880. In 1900 it got serious. By 1925 it was ubiquitous. Jet planes, 1940 they were invented. 1950 the first commercial one was built, put in service in 51. By 1960 they dominated the air fleets. Television, actually the technology is very old, there was a long simmering time. Then between 41 and 55 television became popular in the US. So there's always a decade or two. So you see a whole bunch of these. If you look at big government-sponsored things, you have World War II economy in the US. Well, that was 5 to 10 years, right? And an enormous. Ask yourself how many Liberty ships were built, how many tanks were built. In 10 years, a man got to the moon, right? And you needed to establish a brand new technology for that. The US interstate system was built in 35 years. Here in France, you build a nuclear power industry in 25 years, I would argue. In 20 years, I would argue. I don't know the exact numbers. And coal in China came into being in about 15 years. If you look at these numbers, this is Chinese thermal power growing. By the way, the entire US power fleet is 2,500 terawatt hours. So they built between 1980 and 2010 a power grid and a power system which is bigger than the entire US system by a long shot, because you have to add the other ones too. In coal? Yeah, this is thermal. Yeah, so yeah, but by now they are bigger than our system, right? My point here is the time scales you can get to. And I think mass production favors lots of small systems. And I would argue this will not just apply to air capture. You will see a lot of future infrastructures which are massively parallel. And think about it, 1 billion cars are making a lot of the CO, a third of the CO2 we are worried about. So lots of small units are actually interesting. And if
Small units do with the CO2.
they would aggregate around a big well, and a lot of them in one place, you can get about a few million tons of CO2 out of a square kilometer. If you had more, they interfere with each other. So like you have a wind farm with lots of windmills, there has to be a collection system where you sit and you inject right there underground, for example. Or you sit next to a huge solar panel facility and you take all the electricity nobody wants and convert it into methanol, right? But keep in mind the last point. You may in 5 to 10 years get ready, that sort of goes to the old numbers, then build the new infrastructure and maybe get it to grow in 20 years, but you need another 50 years to pull things down. So this is not an excuse not to do anything. This is saying this is the mopping up, this is the street cleaner which cleans the litter off the street we already dumped there. It is no excuse to throw further litter onto the street. We have a lab version which is proven. We have an outdoor operation that's demonstrated, and we are currently designing a next unit. I think there's a year of hard engineering going into this to make it really nice. And I think you can then have a first stage producing somewhere between 1 and 5 kilopascal of CO2, which you can recover with a moisture swing. And from here to manufacturing, I think you need 1 to 2 years for a prototype, 3 years after that to actually build a supply chain, and 4 to 6 years. In years 4 to 6, you can actually do that. And then in year 7, you could build the first wind farm for CO2 rather than kinetic energy. So that's where I see the time constants of it. What is it all good for? One of the things I'm interested in is to convince volunteers to pay for it. And I'm only halfway joking. I don't think, if you think about recycling, that was a voluntary effort. In the US and here, people voluntarily pay for renewable energy, renewable electricity. And so imagine a button at the pump and say for 50 cents extra, I can get my CO2 back, either because somebody filled biofuel into this gas tank, or because somebody pulled the CO2 back out. If it's costing $110 a ton, that would add $1 to a gallon of gasoline. If the oil companies were to share into this with us, because they have an interest to learn how to do that, because otherwise oil has to be abandoned, that would be 50 cents on the gallon, or 12 cents, 14, 15 cents on the liter. I think one could, if you could convince 1% of the population to do that, you would actually have the largest carbon sequestration effort the world has seen so far. Right? I'm not kidding myself that volunteers will actually solve the problem for you, but they will change the political debate. Just like in recycling. Today, in many places, it's mandatory. Right? And that couldn't happen until you had the volunteers first. So, and I actually think there are real business opportunities, even on the voluntary side, because somebody has to do it and gets paid for it. Right? And if you really get big, this is $1 trillion business. And I'm talking with a number of utilities. I'm saying this is a utility of the future because it's a public goods kind of thing. And it's not all of this will be in conventional. And of course, you also reduce your future liabilities. Because sometime there will be a reckoning, and in 2050, it's very hard for people to say, we didn't think that, never mind what Mr. Trump said, people won't believe you if you say in 2020, I didn't know there's a problem, right? So all of this needs to be thought through, and I think I end here. And actually, we have half an hour now for discussion.
So thank you, Klaus, for this talk that will keep us awake at night. So any questions?
How much oxygen is produced? How much oxygen is produced per year? I mean, compared to producing the CO2, because nature recovers it also. How much is that?
If I just store the CO2, then there's no oxygen produced. If, on the other hand, I make a fuel out of it, I give the oxygen back, just like a plant would, right? Because in effect, I have to unburn H2O and CO2 to CH2 again if I want to have my fuel, so the oxygen came back out, right? But keep in mind too, we are panicked over going from 300 ppm to 500 ppm. In the atmosphere on the oxygen, that means we go from 200,000 ppm and moved 200 ppm away. So in the oxygen, this is not yet visible. On the other hand, if you want me to be a pessimist, the total amount of carbon we have in the ground probably would move the needle on oxygen.
I have a question concerning the surface we are needing. I was not bored by your talk, but I did more. I'm very impressed what you said. And I tried to make an estimation which cross-section you need to gather 1 gigaton, with assuming a mean wind speed from 5 meters per second. And I got something like 100 square kilometer.
That's what you have too.
Is this about this is about
We
the
are-
size? We have 100 gigawatt wind energy installed for one. And is this about the amount
We
what
are-
you
we
have
are little-
with 100 million?
We are a little
uh,
smaller than you. We need, for 1 ton of CO2, we need about 60 square meter if the air flows at 1 meter a second through the filter. And that already accounts for the fact that I only skim. I don't take all the CO2.
But you come in the order of magnitude as we have nowadays all wind turbines. We are taking out the energy. This
No,
surface
we
you need
need
also.
we need to go over the numbers. I know we are smaller, because on 60 square meters you would not eliminate 1 ton of CO2 a day. That's too much energy for a 6-meter windmill. So let's go over the numbers. But I'm sure we are roughly 10 times smaller than a windmill.
Okay, I had a question. I wonder, because you seem to think there is no difference between CO2 coming from oil and coming from carbon, or for coal combustion. But I was thinking that isn't it still easier to capture it where it has its highest concentration?
Absolutely.
Yeah.
I'm saying, take the waste management analogy one step further, right? We are the street sweeper. We are picking up all the stuff which literally fell on the street, and that doesn't say you shouldn't put a waste bin in the corner, in the street corner, right? So we are, and I have said this sometimes, we are the capture of last resort. But simply existing already changes the dynamics in the rest of the story. Because now I can threaten the coal plant, if you don't do it, this is how it's going to be done, right? And you pay for it. So they say, well, we can do it more cheaply, right? And I'm sure they can do it more cheaply. So that's why also when I said we go to the full scale right now, this is to come back down in negative emissions. If you want to ask what fraction of today's or a future energy economy would actually get its CO2 back from air capture, maybe 10%. It's the airplanes, it's the heavy trucks, and the ships, which really have no other option. And then, by the way, you want 100 ppm back because you want to come back down. That's the big player, right? But it'd be foolish to let it out and run after it, except in certain cases. If you sit in the middle of a big city and you can't run a pipeline out of it, you may say, in this, as an aside, I think the old coal plant are stranded assets. Because at $30 a ton, they are not competitive against anything, regardless of whether I captured it or they captured it. Right? They are stranded assets, and people will have to figure that out.
Yes, another question. Did I understand well that the device you're building needs a very dry air, so we cannot put it, for example, here. You see it's raining every day. So did I understand well?
Depends how dry is dry. Yes, we wanted this particular machine wants dry climate. We could cheat because we are also sensitive to heat. So if you forced the worst place for me to be would be the tropics. High relative humidity, high temperature. If you are in Sweden where it's cold and wet, I could still load up a CO2 and then would heat up to 40, 50 degrees C in order to release it. And so I do a little bit of a combination of a humidity and a thermal swing. I don't particularly like thermal swings because they cost me energy, right? So I avoid it. But I also would expect that this is not the only answer to air capture. This is ours. And like windmills want to be in a place where it's windy, our particular technology wants to be in a place where it's dry. And dry actually means 50%. There's a real roll-off at around 50% relative humidity. If you are below that, things look good. If you are above it, you really suffer because you can't load anymore, right? And in a funny way, from a chemical engineering perspective, I'm suffering in the pressure I can get to. I'm not suffering in the throughput. If I fall back to 0.5% CO2 rather than 5%, I can run in any climate. But then being at 0.5% wasn't all that much of a win, right? That's only a 10-fold improvement. I aim for a 100-fold improvement.
Excuse me. I want to follow up slightly on your comments about the decentralized version of this technology where everybody has one in his backyard.
No.
Well, You did say there would have to be a collection scheme, and that's what I was wondering if you could.
I would never pay for a pipeline. So I would not put it in your backyard. Now, if you want a soda machine, we can put one in. We can put this in your windowsill, right? One of the old. Sure, but if you wanted that, I can deliver that, right? I have no good idea what the average private citizen would do with the CO2 I can give them overnight in their location. So I expect it to be in locations where you wanted it, either because you wanted it as a useful thing. Your dry cleaners who may use supercritical CO2 could have one on the roof and keep their CO2 supply filled. But in the end, you are in big places out in a location where you wanted the CO2. And so they are small units. They are not necessarily decentralized. And I don't see very many No, decentralized. I can build a system with 10,000 units in one location. I can also put 10,000 units everywhere. If you put 10,000 units distributed, you have to tell me what did you want to do with that CO2. And there are applications, greenhouses, which again, I eat the tomatoes and the CO2 is back in the air. But greenhouses need 1 ton a day device. And that feeds an hectare of greenhouses. Right, so then it's distributed. But if you sit in a field where you inject into a geological storage, you want 1 million tons a year, right? Which means you have 3,000 such units spread over a square mile.
I have a question about the life cycle analysis of your project, because based on literature, I find that you need a carbon content of your energy about 20 grams of CO2 per kilowatt hour. For your installation to be at a 0 net CO2 emission, meaning that for each ton of CO2 that you capture, you emit no more than 1 ton of CO2.
Okay,
so
how many kilowatt hours did I need?
So you need about 46,000 kilowatt hour for each ton of CO2 removed, based on literature.
Not with I don't know who wrote that, but that one's not right.
So it's based on the already existing things, and it's on what exists in the state of the art of the technology. So have you done any life cycle analysis of your installation?
Yes.
On
first
carbon and energy?
First of all, we use 350 kilowatt hours. Not you're looking at carbon engineering. And that indeed is that high.
It says so with 450 kilowatt hours, it gives so you already need improvements in your carbon content of the energy.
That's thermal.
Done.
I give you a very simple back of the envelope. Take not my process to just see that this is not right. I have the dumbest sorbent I can pick, which is calcium hydroxide. I will turn this into calcium carbonate. I need 180 kilojoules per mole to calcine that. In practice, I'll need 250. There are Italian calciners which are 80% efficient. I can show you this in the handbook. So now we have 250 kilojoules, which I absolutely need to make this work. I'm going to, just to be aggravating here, I'm going to use coal and oxygen to make that happen. Now I need roughly 1/3 of the energy, which made that CO2 in the first place. So I end up with 1.3 tons of CO2 in an oxygen after I burnt the oxygen. So I have now 1.3 tons. The coal CO2 is collected. The only CO2 I spit out is the CO2 from the oxygen plant. When it comes to the life cycle in hours, we are effectively consuming oil in the vessel. Right, that's our biggest upfront life cycle. If at the end I burn it because I wanted a little bit of heat, I can even make it useful. But over its lifetime, this thing will roughly collect 1,000 times its own weight. In every cycle it's 1%, and it needs to last and will last about 100,000 cycles. So yes, I have seen these numbers too. These are people who just, there is a very energy intensive process, which is about 10 times what you actually got out of the CO2 in the first place. I agree with that. And that particular process, the only way that process actually works is because their goal is to make fuel in the next step. So they brush this under the rug because the cost of making fuel is even larger.
Klaus, thanks for the presentation. I don't know, it was 1 or 2 slides back. I think you had something about the rate. I didn't quite get to see it enough. Something 50. Yeah, I think that for. Okay, I just wanted to see those last numbers. So
that's big. That puts you into the 100 million units at the 1 ton a day scale, right? Because that would be 36 gigatons a year. And they are, so that's 100 million trailer trucks.
So I did not understand at least one thing. You said that there's a bunch of CO2 that we have to remove from the atmosphere, but you didn't talk a lot about sequestration. And my understanding is that you talked much more about recycling and recirculating CO2 through greenhouses and stuff. So I don't understand why you call this negative emission, because what you capture, you release it just after. So
I just want to point out, I actually said there are 2 things you can do multiple times. One is you need to sequester it. I didn't talk here about sequestration. The bottom line is that 1,500 gigatons need to be sequestered, right? And you have now multiple choices. One is the big one. If you read the IPCC report from 2005, the big one is geological storage. Statoil has put for 20 years now 1 million ton a year in one particular site. If you go to the US, in enhanced oil recovery, roughly 40 million tons of CO2 go underground. Now, most of that is actually CO2 which came from underground. So it doesn't count on your carbon balance, but it's another example where people actually fairly large scale have put large amounts of CO2 underground. I'm the first one to admit that these technologies too are not mature at the scale that they can handle what needs to be handled, but I'm arguing they will never get mature unless you actually try it. Because my guess right now is that you can make a reasonable case that the total number of such reservoirs worldwide are big enough that you can put a large amount of CO2 away. Whether it's enough or whether you have to move to other options. Right now, a good example, which I'm very, very keen on because I was in the early stages involved, in Iceland people injected CO2 into a basalt, which resulted in they demonstrated that they formed calcium carbonate underground. That is a very permanent way of putting it away. Now, Iceland is very exceptional, but it turns out the entire mid-Atlantic rift is exactly the same place, and it has plenty of water because it's underwater. So you could do the very same thing you did onshore in Iceland, going on offshore underground. So I'm arguing in aggregate, there are plenty of sequestration sites you can get into, and I'm arguing if you really want to come back, you actually have no choice. You have to find one of these methods to work, because otherwise we will be stuck at the level we end up with. So for now, I took this nearly as a given in this talk that people will figure this out. If you look at the NETL atlas, it has ridiculously large numbers, like 22,000 gigatons, if I remember it right, of CO2 capacity in saline aquifers in the US and Canada. I think it's an exaggeration. I think it's not the right number. It is certainly not, and I would like to stress that, a proven reserve. And in some ways, from my perspective, that actually, in my view, spells the end of fossil fuels. And I give you a simple analogy. If you look at oil started very slowly in the early 20th century and gradually grew, and the proven reserve gradually grew with it. If you actually have decided that you have to put 1,500 gigatons of CO2 away, you have a built-in demand on day one of 1,500 gigatons. And so anybody who just developed a proven reserve and says, I can put it there, somebody already has dibs on it. I'm predicting that the price of sequestration will not come down until that overshoot has been taken care of, which makes it virtually impossible for somebody else to walk in and say, I have more CO2, which I just generated, and I want to buy this storage capacity. Because think about what happened to oil prices between 1998 and 2008, when China grew a little faster than people thought. Oil prices jumped from $11 a barrel to $150 a barrel in no time. And the amount of oil in the ground didn't change one iota, but our ability to pull it out was just not there. Right? So I would argue the same will happen to you in CO2, and this time around you have this huge overhang of demand, which is there from day one. That's the problem with cleanups, right? They start big because they were big on the day you started, right? Whereas most economic activity starts small. There was one PC and then another PC, and they built a few thousand of them, and now everybody has a cell phone, right? So things grew gradually, whereas here you have the case that you know from day one that it's large. But I think if people ask me whether I'm so sure that this works, and my answer to this is I'm not sure that it works. But I can tell you if it doesn't work, it will cost us an awful lot, right? So we better figure out whether we can make it work. Yes.
And about sequestration of such huge quantity of CO2, what about transforming that into stone or carbonate as Shell studied that 10 years ago?
I don't know whether you know it, but I started that. Right, in 1995, I looked at all the options and I said, seawater is the principle of maximum ignorance. We know that CO2 in the atmosphere is a bad idea. We haven't studied what it does to the ocean, so we think it's a good idea. So we shouldn't do that. And it turns out with ocean acidification, I was right about that. And it has more or less fallen off the table. In 1995, that was the preferred option. Then geological sequestration came on, and a colleague on that first paper, Chris Wendt, made the case while we were discussing all the options. We looked at all of this in 1995. And he said, any method where you need a computer to convince yourself that it's safe, you will never convince the public that it's safe. Right? And I thought that was very astute, and so we went by geological sequestration back then. And we said the only thing which in our view is safe is making minerals. Right? Making minerals is also the Cadillac in that it's the most expensive option of all of them, right? So therefore, my view right now is we take geological sequestration and start with it, not because I like it, but because it removes the excuse that we don't know what to do. I have no idea whether we can do it long enough and big enough, but I think it could be quite big. We'll try it. If it fails, we better keep working on all the other options, including mineral sequestration. And I think sort of the hybrid of injecting into basalt, which then makes carbonates, is possibly the compromise. The way I look at it, if you read that first paper we wrote, we said we do it above ground. And we said mining is not a problem cost-wise. That adds maybe $8 to $10 to a ton of CO2. We can afford that. It's the chemistry. It's miserably slow. And we said, well, we do high pressure, high temperature in a strong pressure vessel. We can do that. It might even work, but you better be out of there in 30 minutes because I can calculate the volume of the pressure vessel, and I can't afford more than 30 minutes or maybe an hour on the outside of that pressure vessel because otherwise it's too big, because the residence time tells me what the volume is. So therefore, that was the problem. Now, if you go to injection underground and let it carbonate there, I'll give you 25 years, because that's a human time span, right? If I drill back in 25 years and say 5% are still there, I now suck them out and put them somewhere else. We put a line under it and this reservoir is finished. That's something we can do. If it takes 5,000 years, like it does in a standard sandstone, it may as well not happen, right? So then the third option. So that's where we ended up. Somebody has another question, so I better shut up.
Just a little question. Each time you do a cycle, you lose a little of water.
We lose water.
Yes.
And
how much water did you lose, and how much?
It's roughly 10 to 1.
Sorry?
It's roughly 10 to 1. So compared to bio methods, which lose roughly 1,000 to 1, we look really good, right? Because we don't have stomata opening up. But we also get something for that water. That water was fuel, and I cannot get it back. If I get it back, I have to pay it back. So it truly had to evaporate. If it didn't do that, the thermodynamics doesn't work out, right? So, or if I insist on getting it back, then I have to pay the thermodynamics back.
So it's only 10:20, so we have still plenty of time for questions. So, anybody else? Well, really, we did.
You all can leave, but I'd be happy to answer your question. If you take, I may have misspoken because I had to, in my head, convert from gallons, because usually I give the talk in the US. But let's go back. I remember there's roughly 20 pounds of CO2 in a gallon, or roughly, which is about 10 kilograms, which is about 1%, is about 1% of a ton. So you go from $30 to 30 cents if you take a gallon and you divide by 4 once more, and the 30 cents is actually 25 because the pound 20 pounds. For what? Oh, for 600, I'm coming down to $100. So then we're in agreement. No, the $600 is a non-starter. That's a first of a kind process which has to come down. I think you get interesting at the $100 mark. Below that, or €100, above that, you are not yet in the running. But I'm arguing we are not that. That process used blowers, used calcium hydroxide, actually had to convert it from potassium hydroxide to calcium hydroxide, and has to deal with a ton of water.
Question at the end.
Right? So that process is inherently more expensive. Yes.
You know, I was a square meter. I just got an idea just for the end of your talk. So Trump, you must convince Trump. He wants to get a wall financed over thousands of kilometers.
And we'll make him out of this carbonate. And then you won't talk to me anymore. Sure.
So okay, thank you. Thank you. No more questions. Thank you.